So today is the last lecture on community detection in stochastic block model and on exact recovery in particular. And we'll talk about, today we'll finish the proof that the semi-definite program actually exactly recovers the community structure. Okay, so we call the setting. So we have a graph that has n over 2. It's a random graph, n over 2 nodes on each side. You get a connection with probability p inside, and you get a connection with probability q outside. And we think of p bigger than q, right? We focus on this case, and moreover on the regime where p is alpha log n over n, and q is beta log n over n. Right? This is the right regime to look at for exact recovery, right? Where we know if alpha is big enough, at least we know that there's no isolated nodes in each community, right? So this is of course important. Now we looked at the semi-definite program, right? So remember A was the adjacency matrix, right? So A was the adjacency matrix, and we defined B, the signed adjacency. Right, so B was okay, let me write it here. B was simply 2A minus having, right, so at plus 1 if it was an edge and minus 1 if it wasn't. We can write this way. Right, so now, okay, and we have the semi-definite program that we set ourselves to understand was max trace bx such that x positive semi-definite and xii was 1 for all I. Okay. Moreover, what we showed was we wanted to understand in particular when is it that this semi-definite program exactly recovers the true communities, right? And so we define G to be the vector of the true labels. So this is the vector plus or minus n. So these are the true memberships. Right? And we finished last time with this theorem saying that GG transpose, so X equals GG transpose, right, is the optimal solution. So the unique optimal solution even of SDP if there exists a matrix Z that satisfied all these properties. Z was diagonal, right? 2. Z needed to satisfy that, the so-called complementary slightness condition, right? So this was written as something like trace of Z minus B GG transpose equals 0, right? So I'll write here something slightly different, right? Then 3 Z minus B had to be positive semi-definite, and you could only have one thing in its kernel. So which means that the second smallest eigenvalue needed to be actually strictly positive. Now, if this matrix is positive semi-definite, then the only way this happens is if G is actually in the kernel of Z minus B. So actually, it was these conditions, right? So we had these conditions. Now, the strategy, right? And so we reduced the problem of proving whether the SDP exactly recovers a solution to this problem of finding Z that satisfies these properties. But now, here we have, right? What we have here, we have basically n variables and n constraint, n equations, right? Because since the matrix is diagonal, it has n variables. And here we get essentially an equation. So provided there's no kind of degeneracy or anything like this, then we immediately get that, right? There should be, out of these two, there should be only one possible solution. So what we do is we're going to use 1 and 2 to come up with a candidate Z, and then we're going to check whether it verifies 3 and 4, right? So we're going to try to come up with a candidate. Right, so we're going to come up with a candidate Z satisfying equations 1 and 2. Right, so from 1 and 2, what do we have? Well, Z is diagonal, and it needs to satisfy this, so it's easy to see that we must have that ZII, GI, needs to be equal to B, G, entry I of this. Okay, now it actually makes sense to define a few new matrices just to write better what this is. Right, so I'm going to define a couple of extra objects. Right, so we know that D, right, we define D, a diagonal matrix of degrees. Right. Now we're going to do something else. We're going to define DG plus as a diagonal matrix of in degrees. Okay, so this is this has the degree of the node. Entry II of this has the degree of the node as seen just with the connections of the same community, and DG minus will be the same thing but for out degree. Right? So you can write, for example, DG plus, right? Entry II will be the sum for J such that GI equals GJ, right? They're in the same community because remember these were the true memberships of, say, AIJ. Right? And for minus is just with a difference here rather than the equal. Okay, and now we define further a new Laplacian matrix, which we call the stochastic block model Laplacian. Okay, let me erase this because we won't need this for now. Right, so we're going to call this LSVM. This is going to be the stochastic block model Laplacian is going to be equal to the degree matrix minus the adjacency. But the difference here is that we're going to take the degrees to be the in degree minus the out degrees. So we get DG plus minus DG minus adjacency. And notice that this matrix is not, it's not necessarily positive semi-definite, right? In fact, its diagonal elements are not necessarily positive, right? Because it could be that you have more out degree than in degree. But here you're already getting a sense that if this matrix its diagonal is negative, then this is sort of bad news for recovery because it means that one of the nodes is actually more connected to the other community than it is to its own community. So it seems to already be encoding some kind of difficulty of the problem of exact recovery, right? So that's kind of interesting. The other thing I should note is that this does not depend whether we consider self-loops or not, right? If we take a self-loop, it will show up on the diagonal here, and it will just cancel out. So depending whether sometimes it's a bit simpler to just consider self-loops to make the calculations easier, meaning that the self-loop shows up with also probability P, we can definitely do that and nothing changes, right? Only the decomposition changes. Okay, so now that we define this, we can go back to what Z is, okay? So what is Z now? Z, we get that ZII is equal to 1 over GI, right? And now what is this? This is 2A, right? I'm just writing that decomposition, minus 1 transpose plus identity. This times G, entry I. Okay, well, let's see if we can understand better what this is. So 1 transpose times G is 0, right? Because G is balanced, so it's orthogonal to the whole one's vector. G times identity is just GI, right? So we get 1 over GI times GI is just 1. So we have 1 over GI, right? 2, I mean, I can take a 2 here. A, G, into I, plus 1 over GI times GI is just 1. Right? But so what is this? This is just, right? I'm taking AG, all it's doing is it's summing. It's taking the sum over the row of A of AIJ, GJ. Right? But all this is doing is it's taking the ones that are the same, right? And then I'm dividing. Okay, let me write this maybe again. Maybe it's worth doing again. So we get sum over J of AIJ, GJ over GI. But this is 1 when they're in the same community, it's -1 when they're not. So all this is doing is counting the number of edges in the same community, subtracting by the number of edges across community. Right, so this is just 2 in degree minus out degree, right, plus 1. So this means that the candidate, right, the candidate Z is the matrix whose diagonal is twice in degree minus out degree plus 1. So it's just dg plus minus dg minus plus identity. Right, so now we have the candidate Z. So let's write it here. Okay, the candidate Z is equal to C equals to 2 dg plus minus dg minus plus identity. So this is our candidate Z, right? It came from equations 1 and 2. Now what we have to do is to check if it satisfies equations 3 and 4. Right? But it's not hard to see that all you really have to check is equation 4, right? It's condition 4 because we know that G is in the kernel. So if the second smallest eigenvalue is bigger than 0, we know the first one is exactly 0, right? Because the first one corresponds, if the second one is bigger than 0, the first one must correspond to G. So really all we need to check, right? The question is, does the candidate Z satisfy 4? Right, so in particular, we just have to ask ourselves, does lambda 2 of, okay, let's write out this matrix, dg plus minus dg minus plus identity minus b, is this bigger than 0? Right, this is the question really that we have to ask ourselves. Right, and if this is the case, then we know that GG transpose is the optimal solution of the STP. Okay, so let's write down what this is. Right, so what is this? What is this matrix? So we get 2 dg plus minus 2 dg minus plus identity minus, and now 2 a's plus, right, b was that, 2, well, not 2, just 1, right, plus this. Right, so what is this? This is just exactly, right, we get 2 dg plus minus dg minus minus a, so this is just LSBM, or twice LSBM. Right. The identities cancel out, and we get 1 transpose. Okay, so we get this really cool, we get now this really cool theorem, right, that STP achieves exact recovery, or GG transpose is unique opt of STP if the second eigenvalue of 2 LSBM plus 1 transpose is bigger than 0. Okay, so now we reduced our problem, right? Our problem was of understanding what was the optimal solution of semi-effort programming. We reduced that to the problem of understanding whether we could find a matrix Z that satisfied certain conditions. And now we further reduced it to just a spectral condition on a random matrix. Right, so we have now a random matrix LSBM, right? It's random because A is random, and of course the degrees also are random, right? Because they're a function of A. And now the question is completely reduced to a spectral question about this matrix, right? And it's a spectral question that seems to have a lot to do with the positive semi-definite of SBM, or LSBM, right? Because we know the first eigenvalue is 0, right? Because when it's hit against G, it gives 0. So now the question is simply whether this matrix is positive symmetric, and the second eigenvalue actually raises us away from 0, right? And so there's this 1-1 transpose term, which basically is saying that we don't look at what happens, right? There's such a big term here, helping, that we don't really look at what happens in the span of the Waldman's vector, right? It's because originally, in minimum bisection, everything was orthogonal to it, and it's really something about whether this matrix is positive semi-definite or not, right? And here we already see something really cool, which is that if the diagonal elements of this are negative, meaning if one node is more connected to the other community than it is to its own community, then it's bad news, right? Because if we do that, then this matrix will have some negative entries in the diagonal, and we'll just add 1 here, so it won't be enough, and so this for sure won't be positive semi-definite, right? So we're already seeing a lot of interesting features here, but the point is that now we reduced it to an exercise in random matrix theory. Maybe not an easy exercise, but it's not just a question about random matrix theory. In particular, if you wanted to check on the computer, you could just write this matrix and check this condition, right? And then you would know for sure that the STP would give you exactly the right solution. Of course, right? The definition of this matrix, you need to know the clustering to be able to do it, right? But if you just want to understand whether the STP works or not, and you know the answer, you could now check this. But what we're going to do is we're going to use matrix concentration to prove this, right? So the goal, let's leave that matrix on the board. So the goal is to show, right? The goal would be to show, or understanding which parameters that, right? We want to show for ranges of parameters that lambda to LSBM plus 1 transpose is bigger than 0, right? So if we want to understand something about this matrix, right? What is the natural thing to do? What's the thing we have a random matrix, we want to prove something about it, right? We have a random object. So the first thing we should try is to compute its expectation, right? We can ask ourselves, what is the expected value of this matrix? Right, what is the expected value of this matrix, right? This is now, of course, a very, very natural question. Right, so let's write it. So we have 2 expected value of dg plus, right, minus 2 expected value of dg minus, right, minus 2 expected value of A plus 1 transpose. Right, so now we can try to work out exactly what this is. Okay, I might need a bit more room. Okay, so here we'll just to make things easier, we'll just assume that self loops are allowed, right? So with probability p, we get a self loop in the graph as well, right? This doesn't really change anything; it just changes the decomposition. Okay, so what is the expected value of dg plus? So each node is counting the number of neighbors in the same community, right? Each connection shows up with probability alpha log n over n. And you have n over 2 places where you can potentially connect, right? So it's a matrix whose diagonal is n over 2 times alpha log n over n. So it's just n over 2 times alpha log n over n identities. Right. Expected value of dg minus, same thing, but with beta. Right, the probability of connection across communities, and expected value of the adjacency matrix, right? This is a matrix that has p's in the diagonal blocks that correspond to entries that for which I and j are in the same community, and q's on the other one, right? So this is just, we wrote this a few times. This is 1/2, right, times p 1 transpose plus 1/2 times Q GG transpose, right? But here, P is of course, right? So, okay, let's maybe write this a bit more carefully. Right, in the diagonal entries, the diagonal blocks, not just entries, but the blocks that correspond to things in the same community, we get basically this plus this. So we get 1/2 P plus Q plus 1/2 P minus Q. So we get P. In the off-diagonal ones, this is a -1. So we get this minus this. So we get Q. Right. So now we can write this in terms of alpha and beta. So we get 1/2 alpha plus beta log n over n. 1 transpose plus half, right, alpha minus beta log n over n GG transpose. Okay, so now what does this mean? This means that this expectation, right, now we just group all the terms together, is equal to what? Is equal to, we have a bunch of identities, right? We have, well, twice, right? So all these 2's go away because we're taking times 2, right? So we get alpha plus beta. Oh no, alpha minus beta, because this minus that. So we get alpha minus beta log n over n identities, right? That comes from these 2 terms. But then we subtract these 2 of these, right? So we get, let's look at what happens in GG transpose first, right? We subtract twice this, so we get minus alpha minus beta log n over n GG transpose, right? And we subtract this term here too, right? But we subtracted the 1, so this is just the same thing of having plus, and then 1 minus, 1 minus a half, this n cancels with this n, right? I forgot that. This guy goes away. Right, because this minus this, but these n's cancel with this n, and the 2 cancels with that too. Okay, 1 minus alpha plus beta. Okay, so now we can safely ignore, right? We know that this random variable, for any value that it takes, G is always in its kernel. So what happens around GG transpose can be completely ignored. What happens at GG transpose we can completely ignore because it does not matter at all for the second eigenvalue, right? It's completely irrelevant for the sake of the second eigenvalue, right? And so we can safely ignore what happens at GG transpose, and now we just have to look at what's the second, right? Let's try to understand what is the second smallest eigenvalue of the expected value of this matrix. Right? Because, you know, at least we can try to understand what happens in expectation for this. Not in terms of the expectation of the second eigenvalue, but in terms of the second eigenvalue of the expectation. This is not a very natural thing to look at. So what is this? Okay. So we know GG transpose is the stuff that's in the kernel, so we can completely ignore that. And indeed, right? It cancels exactly with this, right? Because notice that G is L2 norm root n, right? So since G is L2 norm root n, this n just makes this abnorm spectral norm or L2 norm 1, so then you get A minus beta log n, A minus beta log n. Okay? So we have a term here, right? And we have another term of 1,1 transpose. Right, but the term of 1,1 transpose, first of all, 1 is much, much bigger than log n over n, so only this really matters. And here we have eigenvalues that are order log n. while here they're of order 1 times the spectral norm of this, right? But the spectral norm of this is n, right? Because 1, transpose is a matrix. The vector of all ones has L2 norm root n, which means that the eigenvalues from here are order log n. These don't matter. And these are additive, but they are of order, right? They're much bigger, right? Essentially, because we're adding this big subtract to this big multiple of all one's vector, it's being visible here that it's making the eigenvalues in this direction be huge, right? They're like of size n rather than of size log n. So it's not hard to see that the second eigenvalue of this matrix will correspond exactly to this number. Right, so what we have basically is that this matrix in expectation has one eigenvalue at 0, corresponding to the direction g, one eigenvalue really large, corresponding to the direction of the whole ones, and all the other ones will be here, alpha minus beta log n. But now we know, okay, let me erase this. Now we know that the second eigenvalue of the expected value, right? Let's look at this matrix. So we have say 2L SVM plus 1 transpose, right? And we know its expected value. Let's say this I'm writing here in terms of the second eigenvalue. Its expected value is up here and 0 is up here. We want to understand what's the probability that it doesn't, we want to bound above the probability that it lands on this side of 0, right? That the second eigenvalue is negative. But we know that the expected value of this matrix lies here. So if we make sure that, a matrix is equal to itself minus is equal to its expectation plus itself minus its expectation, the deviations. And so all we need to show is that the deviations from expectation are not big enough to be able to push the matrix such that in this direction it actually goes below 0. Right, so it's actually enough to show it's enough to show that in deviation, so 2 LSVM minus plus 1 transpose minus its expectation, right? I mean, you can see this as a triangular inequality, right? That this object in spectral norm, right? Because we have to make sure that this change doesn't happen in any eigenvector. Because all it needs to happen is one eigenvector in the direction of eigenvector to push it all the way to negative, and then the second eigenvalue is already negative, right? Because one of the eigenvalues just always fixed at 0. Right? All we need to show is that this spectral norm is smaller than exactly that value, right? Alpha minus beta log n. Right? Because if this deviation is smaller than alpha beta minus log n, then because the expected value of the matrix has all its eigenvalues lying here, then the deviation, if it doesn't have enough spectral norm to push any of them to be smaller than 0, the matrix for sure, the second eigenvalue is bigger than 0, right? I mean, this is triangular inequality. So this means, right, so now we get our matrix concentration theorem, right? So let's write it another theorem. Right? GG transpose is the unique solution, is the unique opt of SDP if this spectral norm is smaller or equal than alpha minus beta log n. But notice, the 1 transpose cancels with the 1 transpose, and the 2, I can push it out. So really, all I need to understand is whether LSVM minus its expectation in spectral norm needs to be smaller than, and now I have to divide by 2. So now this is a matrix concentration question, right? Now we reduced everything, not only to a question in the matrix, but a question about bounding the deviations of a random matrix from its mean, right? Which is the stuff we developed a few weeks ago. Right, so now we reduce the question of understanding when is it that the SDP gives us exact recovery to a question about controlling the deviations of the matrix from its expectations in spectral norm. Which is exactly the kind of thing that we did in the chapter about, in all the lectures about matrix concentration. Okay. So we've been reducing, we reduced from understanding an SDP to finding a matrix that satisfies certain properties to a relation on this, a condition on the spectrum of random matrix to now a condition that looks a lot like a matrix concentration conditions. So now what we have to do is we have to use matrix concentration. Now there is a problem, right? The matrix concentration inequalities we developed were for sums of independent random matrices. Right? It's not obvious that this is a sum of independent random matrices, right? This is defined by you take a graph and then you consider the entries to be some function of the graph. So what we're going to do after the break is we're going to see that this is actually can be rewritten as a sum of independent matrices, and we're going to use matrix Bernstein to get conditions on alpha and beta for this to be satisfied. Thank you.